Modern fluid power systems come in all shapes and sizes. Some are very complex, while others are quite simple. Some systems, like this machine tool, have precision valves and servo mechanisms operating under pressure delivered by a piston pump. High-pressure systems like this need protection from small foreign particles that can cause wear and premature failure of system components. In engine lube oil systems, the principle is the same. The filter protects all internal parts, such as metal, rubber seals, and plastic, from abrasive particles that can cause wear and damage to the machine. The whole purpose of filtration is to protect component parts of a fluid power system from abrasive contaminants that come from the environment outside the machine, as well as from within the system. This cutaway view of a simple hydraulic valve and cylinder will be used to illustrate how abrasive particles in the oil supply shorten the life of hydraulic components. In order to control the cylinder, the valve must divert fluid from one side of the cylinder to the other. As the spool moves within the valve body, it directs the fluid to either end of the cylinder. When it is moved to the right, the cylinder extends. As it is moved back to the left, the fluid in the system is diverted to the other side of the cylinder, and it retracts. Even in this simplest of systems, there are two moving parts: the spool in the valve and the cylinder rod. In operation, the spool slides back and forth in the valve body. The space between the spool and body is slight, with just enough space for a thin film of oil separating the two surfaces. If there were no oil for the parts to ride on, the valve would not operate long before the metal surfaces, rubbing together, would cause small metal flakes to be scraped from the surfaces of the spool and valve body. As these flakes are pushed back and forth by the spool, they roll up into a small metal burr that jams into the space between the spool and the valve body. As the spool continues to move, the burr picks up more metal, making it larger than the space, jamming up the spool as solidly as if it had been welded to the valve body. When this happens, the valve is useless and must be replaced. Now let us look at the valve operating in a normal situation. The spool rides back and forth on the oil film and will continue to operate for years as long as it has a clean, uncontaminated oil supply. Now let us suppose this valve is operating in a system without filtration, and that there is contamination within the system. If a particle finds its way into the space between the spool and valve, it will cause the same problem as a system operating without oil. Any particles in a fluid power system that are harder than metal can cause this kind of damage to hydraulic components. This is because the particles can gouge metal flakes off component surfaces, releasing them into the system. Many times, particles collect on surfaces next to oil seals and O-rings. As the piston rod moves back and forth, the particles make small scratches on the rod. When this scoring becomes deep enough, oil leaks develop if there is pressure in the cylinder. In addition, when the cylinder is retracting, small particles can fill the scratches and enter the system through the oil seal. Common dust and airborne dirt found almost everywhere contain silicas that are more abrasive than metal. The filter continuously removes these particles from the oil supply, protecting the components of the system and ensuring long component life. To better understand how a filter works, let's start at the beginning. The filter is a device placed in the fluid flow stream. There must be holes or channels in the filter for the fluid to flow through. As fluid flows through the filter, it encounters resistance, and there is a pressure loss through the filter. The science of filter design is to achieve the needed protection for the system with the least amount of pressure loss through the filter. This is the job of the media. Media is a term used to describe any material used to filter particles out of a fluid flow stream. The type of media we will be talking about today is made up of a mat of fibers containing millions of channels that allow fluid to flow through the media. This is a photograph of actual media taken with a powerful electron microscope. We can see that the media has depth and presents an intricate maze of flow channels through the fibers. This drawing of a single layer of fibers will help us see how media works. Rotating the drawing to an end view, let's see how the fluid must change direction to flow into the channel between the fibers. To better illustrate how the media traps particles, we will view the space between the fibers as a small tube called a pore. Here we can see how the fluid changes direction to flow into the pores. This action is taking place over the entire surface of the media. In fact, the sole purpose of media is to cause the fluid to change direction. It is this action that actually causes filtration in a depth filter. There are three basic ways media traps particles. All are a result of altered flow. The first way is caused by inertia and works on larger particles. The large particles suspended in the flow stream are heavier than the fluid surrounding them. When the fluid changes direction to enter the pore, the weight or inertia of the particle causes it to continue in a straight line until it collides with the media where it is trapped and held. The second way media traps particles is by diffusion. Diffusion works on the smallest particles. Small particles are not held in place by the viscous fluid and diffuse within the flow stream, as illustrated. As they traverse the flow stream, they collide with the media and are trapped. The third way media traps particles is by direct interception. Direct interception works on particles in the mid-size range. Not quite large enough to have inertia and not small enough to diffuse, these mid-sized particles follow the fluid flow stream as it bends into the pores. Particles along the edge of the flow stream collide with the media and are trapped. We have been looking at a single pore. Looking at actual media, we can see that there are millions of pores arranged into a complex maze. As fluid flows through this maze, presented by the media, it is constantly changing direction. Throughout this maze, the three basic principles of filtration are taking place at every pore, trapping particles and protecting the system. The size of the fibers and pores in the media determine what size particles will be trapped and how many particles can be held before pressure loss requires it to be changed. High-pressure systems, using piston pumps and precision components, must be protected from microscopic-sized particles. As we said earlier, we want the least amount of pressure loss with just the right amount of filtration or needed protection. This is why there are many media choices, each designed to do a specific job for any given application. Before we conclude this presentation on basic filtration principles, let's talk a little about size relationships. We have talked a lot about microns. First of all, what is a micron? The full name for a micron is micrometer. A micrometer is 1/1,000,000th of a meter. In fact, a micron is so small it can only be seen with a microscope. In our example, we talked about 10-micron particles. A 10-micron particle is very small, about the size of a red blood cell. Human hair is usually 50 to 100 microns in diameter, while a single particle of cigarette smoke would be about 1/2 micron. In fluid filtration, we are talking about small particles. In the world of contaminants, fine silt, cement dust, coal dust, and microscopic metal filings all fall within the 10-micron size category. This concludes the presentation on basic fluid filtration.